students, in this video we are going to start third chapter, sequence and series of functions. Okay, first of all we see what is a sequence of functions. All of you are familiar with the sequence of real numbers. Okay, sequence of functions, sequence fn means what? f1, f2 and so on up to fn plus 1 and so on are all functions. That's why this sequence fn is called sequence of functions. Okay, let us see one definition. Pointwise convergence of sequences, pointwise convergence of sequences of functions. Definition first is, there are two definitions for pointwise convergence of sequence of functions. First definition is, let sequence fn n runs from 1 to infinity. It is a sequence of functions where f1, f2 and so on up to infinity, they are all functions. Sequence of function, not only function, it is a real valued function. On a set E. Real valued function means what? Fn is a function from A to R, where codomain is set of real numbers. Okay. Real valued function on set E. We say that sequence fn n runs from 1 to infinity converges to the function f on set E if limit n tends to infinity fn of x is equals to f of x, where x is belongs to E. Let's call this equation number 1. If equation 1 holds, we say that sequence fn is a sequence of functions converges pointwise to f on E. Okay. For if equation 1 holds, then for all x belongs to E, or for every point x of C, the sequence fn n runs from 1 to infinity. The sequence fn, you can write sequence fn or fn of x, both are same, of real numbers converges to f of x. Very simple. Let sequence fn be a sequence of real valued functions on set E. We say that the sequence fn converges to the function f on E if limit n tends to infinity fn of x is equals to f of x. So if equation 1 holds, means if limit n tends to infinity fn of x is equals to f of x, then we say that sequence fn converges pointwise to f on E. Okay, and if equation holds, then for all x belongs to E, the sequence fn of x of real numbers converges to f of x. For better understanding, we will see some examples. First example is find the limit function of the sequence fn of x n runs from 1 to infinity, where fn of x is equals to x raised to n. 0 is less than or equal to x is less than or equal to n. Solution. Students, here note that one thing. If limit n tends to infinity, fn of x is equals to f of x, at that time this f of x is called the limit function of this sequence fn of x. Okay. So we have to find limit function of this sequence of function where fn of x is equals to x raised to n. This is a sequence of function. Means what? You will get f1 of x is equals to x. f2 of x you will get x square. f3 of x you will get x cube, and so on. Okay, means you will get fn of x is nothing but x, x square, x cube, and so on. It is a sequence of function. These are not a real number. Okay. So see here how to solve this type of problem. We have fn of x is equals to x raised to n. Okay. So here we have to check the pointwise convergence of this sequence of the function. Okay, then we will get the limit function for this function. So see here, students, here your axis lies between closed interval 0 1. Means what? Here you will get 3 cases. Here we will check pointwise convergence. So first we will take for x is equals to 0. For x is equals to 0, fn of x will be x raised to n. Sorry, it is a 0 raised to n. So it is 0. So we will get limit n tends to infinity fn of x is equals to 0 when x is equals to 0. Okay. This is the first case. In second case, suppose x is lies in open interval 0 1. For 0 is strictly less than x is strictly less than 1, fn of x will be x raised to n. So limit n tends to infinity fn of x is equals to limit n tends to infinity x raised to n. But your axis lies in open interval 0 1, and we know that when x lies in open interval 0 1, and as we take limit n tends to infinity, this term will be 0. Okay. Third case, for x is equals to 1, your fn of x will be 1 raised to n, it is 1. So limit n tends to infinity fn of x is equals to 1. So here we will get limit function f of x is equals to what? 0. When we get 0, if x is 0 is less than or equal to x is strictly less than 1. Okay, in these two cases we will get f of x is equals to 0 and 1 when x is equals to 1. Okay, so the given, therefore the sequence fn of x and runs from 1 to infinity converges pointwise in closed interval 0, 1. Okay, let us take one more example. Let us take second example. Find the limit function of the sequence fn of x where fn of x is equals to x upon 1 plus nx. Okay, here your x's lies in semi-closed at 0 and semi-open at infinity. So here we will find limit. Here fn of x is equals to x upon 1 plus nx. Here we will not checking at x is equals to 0, then x is belongs to semi-open at 0 and open at infinity. Here we will find directly. Okay, so what we will get? X upon 1 plus nx. Okay, therefore limit n tends to infinity fn of x is equals to x upon 1 plus nx. Okay, where your x is 0 is less than or equal to x, which is strictly less than infinity. Okay, as n tends to infinity, what happens? Sorry, here limit n tends to infinity. Limit n tends to infinity. What happens? As n tends to infinity, denominator becomes infinity, and something upon infinity you will get 0. Means what? Limit n tends to infinity fn of x is equals to 0. When 0 is less than or equal to x is strictly less than infinity. Therefore the sequence of fn of x and runs from 1 to infinity converges pointwise to f of x in interval 0 is less than or equal to x strictly less than infinity. In interval semi-closed at 0, it is open at infinity. Okay, let us take one example for homework. Find the limit function of the sequence where fn of x is equals to nx upon 1 plus n square x square. Interval is minus infinity to infinity. Okay, take this example for homework. Let us see second definition of pointwise convergence. The sequence of function sequence fn, n runs from 1 to infinity, converges to f on the set E if for each x belongs to E given epsilon greater than 0, there exists n belongs to I, where I is set of positive integers such that mod fn of x minus f of x is strictly less than epsilon. N is greater than or equal to capital. Call this equation number. In general, the number n depends on both epsilon and x. It is not always possible to find n such that one holds for all x in E simultaneously. See here, students, what is the second definition of pointwise convergence? The sequence of functions fn converges to f on the set E if for each x belongs to E given epsilon greater than 0, there exists n belongs to I. This I is not a set of integers, it is a set of positive integers such that mod fn of x minus f of x is strictly less than epsilon. In general, this n is depends on both epsilon and x. Okay, it is not always possible to find n such that one holds. What is the definition 1? Definition 1 is if limit n tends to infinity, fn of x is equals to f of x for x belongs to E, then we say that sequence fn is pointwise converges to f of x, and this is the second definition. Okay, now we will solve some example based on this definition. Okay, so let us first example. First example is let fn of x is equals to sin nx upon n. 0 is less than or equal to x is less than or equal to 1. Thus there exists n belongs to I such that mod fn of x minus 0 is strictly less than 1 by 10. Here n is greater than or small n is greater than or equal to capital N for all x belongs to closed interval 0 1 simultaneously. Solution. See here, students, we have given this sequence of functions fn of x is equals to sin nx upon x. We have to find out, or does there exist n belongs to I such that satisfies this inequality for all x's belongs to closed interval 0, 1 simultaneously. Okay. Here we have fn of x is equals to sin nx upon n. Okay. X's belongs to closed interval 0, 1. First of all, we will find limit function for this function, sequence of function. Limit n tends to infinity, fn of x is equals to limit n tends to infinity sin nx upon n. X's belongs to closed interval 0, okay, which is equals to, this can be written as limit n tends to infinity 1 by n into limit n tends to infinity sin nx. Okay. Limit n tends to infinity, you will get this value 0, and you will get this is a some finite value, okay, into limit n tends to infinity sin nx. So this will be a 0 because sin x, your x's lies in 0 and 1. So your sin x will be lies in -1 and +1. Means you will get here finite value, and 0 into finite value you will get 0. Or here you can see that if you put limit n tends to infinity, you will get this as sin nx is a finite value, and upon infinity, something finite value upon infinity, you will get a 0. So this limit is a 0. So we will get f of x is equals to 0. Therefore, sequence fn of x, n runs from 1 to infinity, converges pointwise to f of x is equals to 0. X is belongs to closed interval 0, 1. Okay. Now, but we have to find is there exist n belongs to I or not. Okay. So I will rub this all. Now to find n belongs to capital R such that mod fn of x minus f of x. Now use second definition of pointwise convergence, strictly less than epsilon. N is greater than or equal to capital N. Here fn of x is mod of sin nx upon n minus, here f of x is 0, which is strictly less than epsilon. N is greater than or equal to capital N. Modulus of or mod of sin nx upon n minus 0 is sin nx upon n, which is strictly less than epsilon. N is greater than or equal to n. And here we have given already epsilon is 1 by 10. So here is 1 by 10. Okay. Now simplify this for small n, then you will get a value of capital N. Okay. But we know that, students, modulus of sin nx is always less than or equal to 1. Okay. X is belongs to closed interval 0, 1, and n is greater than or equal to capital N. So this value is 1 upon n, which is strictly less than 1 by 10. Take reciprocal of both sides, you will get n is greater than 10. Means what? This small n is strictly greater than 10, means you have to choose next integer, which is 11. So we can take n is equal to 11. Okay. So here value of n is 11. For n is equals to 11, this for n is equals to 11, we will get mod fn of x minus 0 is strictly less than 1 upon 10. Okay. Here condition is n is greater than or equal to capital N. Okay. Let us take next example. Let f of n is equals to x raised to n upon 1 plus x raised to n. 0 is less than or equal to x is less than or equal to 1. Show that sequence fn n runs from 1 to infinity converges pointwise on closed interval 0 1. If f of x is equals to limit n tends to infinity fn of x 0 is less than or equal to x is less than or equal to 1, does there exist n belongs to I is set of positive integers such that mod of fn of x minus f of x is strictly less than 1 by 4. Small n is greater than or equal to capital N, and for all x is belongs to closed interval 0 1 simultaneously. Okay. Solution. See here students, first we have to show the sequence fn converges pointwise on closed interval 0, and then we have to find capital N. Okay. Here we have fn of x is equals to x raised to n upon 1 plus x raised to n. Okay. So limit n tends to infinity fn of x is equals to limit n tends to infinity fn of x. Okay. Is equals to limit n tends to infinity x raised to n upon 1 plus x raised to n. 0 is less than or equal to x is strictly less than 1. We will find limit when x is greater than or equal to 0 and less than 1. At that time, see here, when x is 0, at that time you will get 0 upon 1 is 0, means what? Limit n tends to infinity fn of x is equals to 0 if x is equals to 0. Now, when x is belongs to open interval 0 1, at that time x raised to n is 0 and x raised to n is also 0. So we will get again 0 upon 1 is 0. So here we will get this is a 0 when x is 0 is less than or equal to x is strictly less than 1. Suppose this is the first case, and second case is when x is equals to 1. At that time fn of x is equals to, if put here x is equals to 1, you will get 1 upon 1 plus 1. This is nothing but 1 by 2. So limit n tends to infinity fn of x is equals to limit, or I will write directly here, you will get this limit is 1 by 2. Means what? You will get f of x is equals to 0 if 0 is less than or equal to x is strictly less than 1, and 1 by 2 if x is equals to 1. Okay, this is the limit function. So that's why sequence fn of x converges pointwise to f of x in closed interval 0 1. Sorry, here is closed interval. Okay, now to find n belongs to I such that mod fn of x minus f of x is strictly less than 1 by 4, where n is greater than or equal to capital N. So what is fn of x? Fn of x is here x raised to n upon 1 plus x raised to n minus f of x is 0. Here we have two values, but we will choose 0